We have four different ideas right now that we've developed for electrical phenomena. We started with Coulomb's law, which was introduced in the force that is exerted upon charges. We later developed that into an electric field, which doesn't discuss interactions, just discusses an influence over the environment of charges. Right? And then we decided to dabble into energy, which eventually led us to the concept of potential. We started with the force up here, and we've eventually got our way down to potential. And potential is the most practical quantity that we're going to work with. So it took a while to get to this point, but now that we're at this point, we can start to develop that. Now, one thing we have not really done, though, and you saw a little bit of this in the lab on Friday, is you want to explore a little more the connection between the electric potential and the electric field. Okay, and that's really what the purpose of today's lecture is going to be. We sort of know how to get there because the way we got potential was talk about energy, and energy was derived from forces through work. Right? We did an integral of force to distance, and that provides us a statement of work, which is related to potential energy, and then from there we define this quantity called potential. All right, potential difference between 2 points in space, it can be determined through your electric field. What this equation is, so you saw this in lab a little bit, but you probably wonder, like, what the heck is this equation? I don't know anything about this equation here. Well, let me tell you. This equation is, this integral here is basically work. If you want an F here instead of a delta S or ds. I'm sorry, you want an F here instead of an E. But we know what you're going to get when you do this. You're going to get a statement. If you have F here, you're going to get a statement about work, which is related to potential energy. So if you divide out your test charges, so to speak, which are constants, then you have a very different expression here. Now you can change this from an F to an E, and then the work, which is related to potential energy, can be turned into potential difference. And so this is a very important relationship, very, very important relationship that relates how the electric field creates a potential difference. Now, there is a negative sign here. And the reason why this negative sign exists is because it meant to communicate. It's meant to communicate that as you move along the direction of the electric field, the potential energy drops. So that's why this negative sign is placed here. Okay. All right. Now, it's an integral, right? And so we can actually do the integral from an analytical standpoint, or we can investigate how the graphs look. In the interpretation graphically of the integral is the area that is bounded by the electric field graph, okay, by the electric field function, so to speak. Notice this down here says an E sub S, and this S is a generic direction. When you do this, you have to specify a path, right? And that path is going to be in some random direction. It could be X, could be Y, could be R, whatever you want, right? So let's just start doing some examples here. We are given an electric field graph. So for whatever reason, our electric field is going to increase linearly. Linearly. I think that's how you do it. All right. Which we've seen that, right? If you are inside, for example, a charge insulated sphere that has charge distributed throughout, we found that the electric field increases linearly. Okay. So what we can do is we can determine an expression for the electric potential based on this. Now we are going to integrate this, so you know what you get when you integrate a linear function. You get a quadratic function. So let's go ahead and look at how this is going to go here. Now, to calculate the area here is very simple. I mean, we could, if you really wanted to, develop a function for this. Unfortunately, a lot of people come out of calculus and they want to turn everything into functions and then integrate them or take derivatives of that. And that is frowned upon, unfortunately. You can do that. You're kind of missing the point if you do that. You don't want to turn everything into a bunch of things you remember from math. I mean, you could. I mean, that would be easy to do here, though, right? I mean, because your function is what? Volts per meter, meter. Yeah, it's just 1,000x. That's easy to do, right? Yeah. Don't sing. People singing in the background. Don't talk to you? All right, I won't talk to you then. All right, so here is what this will look like. This now it's a parabola, but it's flipped, right? Because the negative sign that's outside the integral. And so as you see here, if we integrate that analytic expression, now I just went on about how you shouldn't do this, but we're doing it just because it was so simple to do. Otherwise, I don't recommend it because it's tricky. It is very tricky. But if we integrate this, then we end up with a negative 500x squared here. But you also can derive that from doing your areas, because if we take the potential to be 0 at 0, then our potential difference is just equal to the final potential. So that's what our graph's going to look like here. And so what's the area under the curve? Well, it's a triangle, right? And the triangle has a base of x, and the height is whatever lies on that linear line, so that's 1,000. So this is, it's kind of doing a weird, it's doing the integration based on how areas are done, but you can get it both ways. But do realize that this is, this opens downward, right? Because as you get farther away, the potential should be decreasing. So for whatever reason, our potential in the center of this thing is 0. I don't know why that is, but whatever. That's just the way it is. All right. We're going to do a lot of examples of this stuff, so buckle up. This is the graph of the x component of the electric field along the x-axis. So what do we got here? We got a linear function again, but this one is decreasing. Right? The potential is 0 at the origin, so what's the potential going to be at 1 meter? Put it in the chat. Let me know what you think. It's a triangle. All right, 1/2 times 1 times 2,000 is 1,000. Put a negative on there. All right, put a negative on there. And answer C. All right, let's do another example here. The potential at the origin is a minus 50 volts. Generate a potential graph from the electric field graph that is given. Okay, so what is our electric field doing here? It is a constant as we go from 0 to 2 meters, and then it starts to decrease linearly for the next meter. Right? So what I'm going to do, I'm going to do this in pieces. You might remember something like this way back in Physics 110, at least you had it with me, where we worked out like positions from velocity graphs. It's the same idea. So let's look at how this one's done. Where's my slide? It's a weird day. It's a weird day today. All right, so I'm going to do this in pieces here. On the left here, I'm going to work out, this thing right here. For every meter, I'm going to work out what this integral is. Taking my initial potential, subtracting off the piece of area I'm considering, working out a final. So I can work out a potential at 1 meter, 2 meter, and 3 meters by just adding up these pieces. Okay. Now I'm trying to develop a graph, right? So to do that, I got options here. My options are to, turn these into functions and integrate them. Not a good idea. Like this linear part here, I mean, if I make you do that, you're probably going to screw that up. Because you got to realize there's a y-intercept, right? It's somewhere way up here. You got to figure that out. You got to figure out the slope. You got to figure out the y-intercept. Don't do that. That's unnecessary. Here, my potential at 0 meters is negative 50. So when I go to do V1, it's going to be the initial potential, the one that was at 0, minus the area between 0 and 1. Now, each square here, I know it's a little hard to, okay, so it's kind of hard to see these lines. Let me, there we go. There we go. That's okay. Then we got one going like this. Okay. So each one of these boxes apparently is 100 volts. The area for the first part here, 0 to 1, is 200. So we end up here with a minus 250 volts. Then what I'm going to do is, what I decided to do here is I'm going to evaluate at different points, but I'm going to always keep the initial at the minus 50 because I'm generating points here, right? So I'm always comparing to the initial value here. So when I go out to 2 meters, the area becomes 400, so I'm at negative 450. When I go to 3 meters, this triangle that's here is 100, so I end up with a minus 550. All right, so let's go ahead and plot those points. If we plot those points, oh, come on. Come on. We started at negative 50 right here, and as you can see, oops, it's kind of hard. Ooh, it's kind of hard to get down there. All right, we got it. It's hard to see, but as we get down here, it's linear, right? Because we were flat originally. We were a constant. Now we're integrating, so we're linear for a while. And then we get to the point that decreases. Now we end up with a little bit of a parabola here, and these things got to join up. All right, and so we end up with this. This is what our potential looks like. All right, fantastic. All right, so again, what I did here is everything is based on this initial relationship right here. And that's how we're doing our integrations. We're not going to actually integrate something empirically. No, that's not the word. What's that word? Analytically? I don't know. I don't remember the word now. All right, let's move on. Let's move on. That is not the right slide. This is the correct slide. All right. Now let's get down to, now that we've seen this relationship here, delta V equals minus the path integral of the electric field. Then we start reconsidering, what is going on with this potential? What ultimately is happening here? Well, electric fields are the result of the presence of charge, right? And anytime you have a separation of charge of any kind, you create a potential difference. Basically, it could either be charge located in a particular spot, and you evaluate a point that's away from it. So there's some separation there from the charge, or there's actually a separation of charge on both sides, a positive and a negative. So here we have these, I don't know, let's just call these things electrodes here. You have a positive and the negative electrode here. And there will be an electric field between these things. You actually saw something like this in your lab where we had established a higher and lower potential conductors that were a source of charge and therefore a source of potential difference. And the electric field gets established, and because of that, you can establish a potential difference. And that is going to be, for us, one of the most common ways to develop a potential difference is have and charge separated. Right? That's a very easy way to do that. One of the ways that this is done is through the use of common batteries. Okay, and the way the common battery works is there are some nasty chemicals inside of your batteries, and the chemical reactions create a separation of charge. The separation of charge in there establishes the potential difference. Okay, what happens as you start to use your battery? That separation of charge starts to diminish, and if you have a battery that runs out, a dead battery, so to speak. A dead battery is not a dead battery, right? A dead battery is one that doesn't have the required potential difference to operate. Okay, for example, this always happens. I don't know why my car is just really bad with batteries. It's probably me. I don't know, but a car battery is what, 15 volts? Everybody know? 15, 12? 12? I think it's 12 actually. 12 volts is the normal car battery. Car battery, I think it's 12. And what happens usually is I go to this place on Avenue I. Nice place. 12.6. And so what happens is my battery's being a little funny. Yeah, so what happens is I go take it to the shop up on I, and they test it out, and it comes out at like 10 or 9 or something. And that's not good because the circuits in the car require those 12 whatever 0.6 or above, I guess. Output. And so if you have your AA batteries, I believe AA's are 1.5. When it wears down, you test it. It's probably something like, I don't know. It's lower. I mean, I was just changing out a bunch of 9-volt batteries I had because for some reason I have like 20 smoke detectors in this house. I don't know why. There's so many smoke detectors. Like, there's some smoke detectors that are like. I have one where there's a smoke detector and like literally 3 feet away is another one. I'm like, what the hell is this all about? Anyway, so what happens is every single freaking month the little chirping starts happening. So I got like a stockpile of these 9 volts, and anyway, I test them. If they get down to like 7 or 6, they don't work anymore. They don't work for that, but they still provide a potential difference. You can probably jimmy them up to something else. I don't recommend that, but you can get away with doing something like that. Well, that's what I do. I take them out, and then they just sit around. Like, for the longest time, I just had like wires hanging from my ceiling because I took all the smoke detectors out. And I'm thinking they're there for a reason. Maybe I should kind of fix that, but whatever. Yeah, the whole thing about I know, who needs them? All right, dumb. All right, so but anyway, this is a very common way to get that done. And a rechargeable battery is one where the chemicals allow a flow in the other direction. Of course, that diminishes over time. You can't always achieve the same kind of potential difference when you recharge things, but they work pretty decently. We're not going to get into batteries more than what I just said here, though. It's interesting, but it's more of a chemistry discussion, and chemistry, it's okay. All right. So the way we're going to talk about our batteries, this is going to be our source of potential difference for a very long time, put it that way. We're going to be establishing our potential difference via battery. Typically, we have a Unfortunately, there are moments of the day where you're not awake. So there's a little bit of an issue there. Anyway, okay. So your potential difference for the battery is given with this symbol here. This symbol, which looks like this, fancy E, which it is, it's a fancy E, is called the electromotive force, or EMF for short. Now, this is a terrible phrase, electromotive force. It's a very archaic term that was developed a very long time ago, before a lot of our modern conventions for current was created. By the way, you got to realize, for this class here, the vast majority of our ideas were not developed in the 20th century. Okay? Most of these ideas were developed before we knew that electrons were a thing. And so we have a lot of strange conventions and names for things that don't really mesh with our modern understanding of electricity and magnetism. But there's something that have been used for so many years that we're just kind of stuck with it. And so this EMF here refers to what the battery is able to do. Now, this is an ideal battery. This is what the battery is supposed to deliver. The reality, though, a real battery does have some internal resistance in it, which builds as the battery starts to be worn out. Okay, so this is your theoretical, what the battery is supposed to be able to do. Okay. So when we hook up batteries in what we call a series configuration, and what that means is, it means what it sounds like. Have things in series means they're sequential. So if we have these two batteries here for this light bulb here, not this flashlight. Usually the flashlights take the jumbo D batteries. Things are huge voltage D battery. What is it? Probably something like, oh, they're all 1.5s. I knew that, actually. I always look this up, and I'm always like, oh yeah, I knew that. But yeah, the 1.5 volts for the D battery. Anyway, so what happens here is we simply add those up, and these act in tandem. Right? They act together to produce a 3-volt thing. So you might have a device that requires, 2 or 3 or 4, and it's because they require more voltage. And having the 1.5 is nice because you can create these increments that can provide whatever kind of power you need. So, okay. All right. So now let's look at the other side of our electric to potential relationship here. Now, what we can do with this is, instead of looking at an integral expression to figure out what our potential difference is due to electric field, we actually can work backwards with that, right? Isn't that like fundamental theorem of calculus or something like that, right? We can go backwards, so that means if you can integrate an electric field to get a potential, then you should be able to take the derivative of a potential and work out the electric field. That's true if we look at our expression here, delta V equals minus ES delta S. Now, this expression here is only really true if you have a very small distance here, right? So the fact is that the electric field doesn't vary much over that distance, and you can, at least at that particular location, provide a decent estimate for it. Well, it doesn't become an estimate if you take the limit that the deltas go very small, and they become differentials. So in the limit that your separation distance is extremely small, this turns into a derivative. But you got to be careful about this derivative. Okay? This derivative is a dVds, and that gives you the electric field along the direction of S, which is not the entire field. So you had a complicated field. So you had a field that varied with, say, X and Y and Z. Something really wild, right? And if you had information about what the potential differences are at various locations, you could work out the electric field along a particular direction. You wouldn't be able to work out what the entire field is necessarily, at least not yet. Okay, So just to put this in action here, let's just see that this works to figure out the electric field of a point charge. Now this may seem a little silly because the whole reason we got this expression up here to begin with was because we did an integration. So, but still, we can still apply this. So the electric field along the r direction is going to be given by minus dV dr. We put in our expression for the potential as a function of r. We take that derivative there. There's a negative that goes out to the front. We subtract off 1 and we get a 2 down here because remember these are negative exponents. And we end up with the expected electric field of a point charge. So that works out very nicely. Well, one of the reasons why this works out nicely is because this is the only component of the electric field, right? We defined a radial component and there's no other component. So not only is this E sub r, but we could now just take off the r, put an r hat here, throw a little vector cap on our electric field, and there we go. We got it. So let's do that here, right? Let's do that. We're going to go backwards now. We're going to start with our potential graph, and we're going to work out what the electric field is at these 3 different locations, because you have these kinks here in the graph, which means you have some sort of abrupt change in the behavior of the field here. So we're going to take these in pieces. So we're just basically working out the slopes. That's the graphical understanding, right? If we go back here, you know, what's the graphical understanding of this? Well, the graphical understanding is that the electric field is the slope of the potential graph minus, right, the slope of the potential graph. So this first part here, what's that slope? Looks like it's 20 over 2, right? So that's a 10. Oh, no. Uh-oh, look. Uh-oh, messed up. Look at this. Centimeters. You know what? Look at this. This is cool. The green on my Zoom stuff, it's a little lighter actually. That's interesting. Let's just look at my example then, because things are in centimeters here. We gotta be careful about that now. So, EX, this is the x direction, and you gotta make sure you put things in meters because we want our electric field to be volts per meter. So our difference in the top is 20. We go from 0 to 0.02 meters, and we end up with a minus 1,000 volts per meter. Now the electric field would be a constant. Sorry, the potential. The potential is constant here. That means the electric field is 0. Right? There's no change. Slope is 0. The electric field is 0. And then this other section here, this is a negative slope, so we should end up with a positive value for our potential. And that's 20 over now what? Double that. Double what we had in number 1 here. So that's 500 volts per meter. So the graph looks like a step function here. We go from 1,000, minus 1,000 to 0 to positive 500. Okay, so this is evaluating just slopes. We've done that many times before. Okay, that was this. All right. Ooh, this is good. At which point is the electric field stronger? Let me see. It's A. It is A. Why? Slopes, right? So let's look. What is... I'm going to go with lavender now. Let's just change the... Lavender. This is like a lavender here. By the way, the lime green, look at this. Let me just do this. Okay, I've got a bunch of these. And then look at the lavender with it. Oh, man. That's pretty. That's a nice color scheme. You don't really see that kind of color scheme. All right, so we're looking at slopes, right? So let's say if I evaluated XA, what do we got here? I got a slope that looks like that, right about there. And then XB, we got a slope that looks sort of like this. Okay, now the slope at XA is greater, so the electric field's greater. That's simply it. Okay. Another question for you here. Electron is released from rest. This is a great question, by the way. This is the kind of question. I kind of wish I didn't show you this question because this is one of those questions I'm like, this is for the test. This is for the test. That's a test question. I love these questions. Electron is released from rest at x equals 2 meters. Where? Right here. Oh, potential 0 there. Crazy. What does the electron do after being released? Excellent question. Let me see what you think. Now, check this out though. This is an electron. Electron. I was grading something. What did I grade? I graded something on Saturday. Gosh, what was it? Well, you guys really messed up. Whoa, oh, gosh, I can't remember now. Anyway, I graded some homework over the weekend, and most of you got it because this particular question wrong in the homework. Or was it in the lab? Oh, it was in the lab. It was the electric field lab. That was a nightmare to grade. A lot of you got things wrong because you didn't notice it was an electron. So anyway, the answer here is, Okay, so what do electrons do? They go higher potential. Whoa. Ooh, these aren't the same options. What happened here? Ooh, I'm a little confused. What happened here? Okay. I'm so confused. I don't know. Sorry about this. I don't know what happened. I think it was sabotage. I think one of my kids probably sabotaged my lecture. All right. No video games for 3 months. Here we go. All right. Move to the left with increasing speed. That's true. It's a negative charge. The negative charge wants to move towards increased potential. Right? That's movement to the left. Okay. Now, what happens is, it says increase in speed. Now, steady speed means constant. It's not constant, right? Because the force is not constant. Right? If we have a potential difference like we see here and it changes, the electric field is changing, therefore the force is changing. And as the potential increases, all the other quantities increase. So we have a movement to the left with an increase in speed. And again, the key here is this is an electron. And electrons want to go towards a higher potential. Now, we could also think about this in terms of the slopes and things like that. So if we do that here, we find that the slope is going to look like this right here, something like that. But the electric field, that's a negative slope, but the electric field is going to be minus that slope, right? So that's actually a positive value of the electric field. It means it's going to be pointing to the right. That means the electron moves to the left. Okay, that's kind of what I mentioned over here. Excellent. Very good question. Almost worthy of your test. It needs to be a little bit more confusing, a little bit more difficult for it to be worthy of the exam. Okay, my intention is when you read these questions in the exam, the first thing that comes to your mind is, what? Is this even, do I have the right class? Is this the right class? And if I'm doing that, I'm doing my job. I'm just kidding. In 3 dimensions, we got this thing here. Now, for those of you savvy enough that have taken some vector calculus, you might know what this is. This is your divergence. And it involves partial derivatives. Before I say that, I better make sure I'm right about that. Div definition. No, math. No, it's math. It's a divergence, I'm positive. But there's another one that's upside down, which is called the, what's the one that's upside down? The del? Div and del? Am I dumb here? No, it's div. It's div. So it's the yeah, okay, it's div. But you know, you don't know this stuff. I'm showing you this, and you don't really know what this is because the requirements for this class is Math 160, and you haven't seen this yet. So, I mean, it's partials. Don't worry about that. The idea is that if you look, there are three terms on the left, and there are three terms on the right, and the I hats and J hats and K hats all align. And all this is really saying is this: if I take the derivative with respect of the potential with respect to x, I'll get my electric field in the x direction. There's partials here because while y and z are variables, when we take the derivative, we treat them as if they are constants. And that's really it. That's really all that means. Okay. I don't know why, you know, we do partials, you know, if you remember, there was a time where we were on campus. When I say campus, there are buildings in a location where we would go to do class. I don't remember that, but when we did labs, like the first lab has a partial, and everybody freaks out about the partial. So, yeah, they're actually it's over on K, and I don't even remember now. I haven't been there in a long time, but there are buildings where you can do the same thing that we're doing here, but we're all together. Right? We're all in the same room, actually. Which, if you think about it, that makes like a lot of sense, right? Like it makes so much more sense. Yeah, I know, right? All right, so I don't know. Maybe we'll do that again. I don't know, but that was we did that. Yeah, I know we did that a long time ago, though. Things have changed. You know, this is 2020. You know, trying new things out all the time. Okay. Oh, right, COVID. Oh my gosh, I forgot. Okay, yeah, COVID. All right. Whew. I was wondering, like, why don't we do that again? Okay. Yeah, I don't want to get COVID. Don't want to get COVID. Okay. I think I got COVID way back in March. Way back in March. For me, it just tickled. So I was lucky. But my sons were not so lucky. They got very, very, very sick. And this was back before you could get tests. So I don't know. It could have been a flu. But it was weird. It was weird how sick they were. And it was classic symptoms. Anyway, all right. So, excellent question here. We have an electric field that points to the left. And the length of the line, these are vectors, right? So the length of these lines are indicating the strength of the field, right? So if the vectors get short, the field is weaker. Okay, so given that the electric field points to the left and decreases in magnitude as you move to the left, what would be the correct equipotential surfaces? Remember, what you're keeping in mind here is dV dx, right? Minus that is your electric field. So think about this. C's, a lot of you like B. A lot of you like B. Oh, there's another C in there. Let's look. Can we rule things out? Let's rule some things out. All right, let's rule some things out. I don't like A or D at all. So they're gone. Why? Because they're showing equally spaced lines, right? And that would mean, if they're equally spaced lines, that means your electric field should be a constant. No, it's not a constant. So that's wrong. What about the concept that potential decreases as you move along the electric field direction? Okay, well, that means I don't like E very much, and I don't like F, because it's indicating that my potential is increasing. So my options are now B and C. And what do we got here? We got bunched up lines on the right, and C has bunched up lines on the left. What does it mean for the lines to be bunched up? What that means is the same potential difference occurs over a very small space, which would indicate a large electric field. So the interpretation here is that the left-hand side for B is a larger field, and for C, sorry, the right-hand side on B. the left-hand side on C. So it looks like the answer is B. I'm going to say C is wrong. I hope I'm right. I hope I'm right. Because I'm your teacher, and I'm the one that should be getting things right, right? Oh my goodness. Thank goodness. It is B. So the lines are not equally spaced. Good. The potential decreases as you go to the left. Good. The lines are bunched up on the right-hand side. Also good. All those things work out. Fantastic question. Fantastic analysis, if I do say so myself. We're riding A's and C's and C's and A's and B's. What about D? You don't like D? Okay, let's look at it. Let's analyze this. All right, our electric field at the dot. Okay, this points to the right. That's nice. Equally spaced. That's fantastic. Well, let's figure out an interval here. Let's see. We go from 40 to 20 over 2 meters, right? So the ratio there is going to be 20 over 2. That's 10. So it's A or B. The electric field is positive here, so the answer's got to be B, because the potential... Wait a minute. It's A. Why do I have the direction already here? There shouldn't be an arrow here. I fouled this up. It's A. Okay, 20 over 2. That's what's going on. I should need to take this arrow out. This question's not very good because it automatically says that B and D are wrong. So if you said B or D, gotta pay attention to my mistakes here. All right. This problem I thought was a lot harder, but it's not. Now, by the way, it says, oh, I know what I was going to say here. The electric field at the dot. Well, at this dot, anywhere, right? This entire region has this electric field because it's a constant, right? The electric field is constant here because we have equally spaced equipotential lines. Good analysis. All right. So, now, that being said, we can come up with a really interesting relationship here. Now, at the core of this relationship is the knowledge that the electric force is a conservative force, which means there is a path independence here. Okay? Conservative forces have associated potential energies, and they have a path independence to them. So if I want to go from point 1 to point 2 here, I can go from 1 down to this point D here, which is going to be an increase in 20 volts. Then if I travel along the equipotential line, there's no work required because there's no change in energy there, and I get to 2. And that's one way I can go about doing it. If I take this other path, which is blue, I go from point 1 over to A, and again, there's no energy required to do that because I stay along the equipotential, and then I go from A to B, which takes 10 volts to do. B to C is 0 volts, and C down to point 2 is another 10 volts for a grand total of 20. So going from 1 to 2 is going to produce a 20 volt increase. Now, are those the only paths I can take? Certainly not. I can take this path right here. I can do that. What else can I do? I can do this path. I shouldn't use red. We already have a red. How about we do a... How do we do yellow? Let's go for yellow here. I can go up like this and down like this. I can do that one. Let's do white. I can go this way, and then I can go this way. You see that? You don't, because I did white. Huh. Anyway, so what's this mean is this. What if I decide to loop around then? If it takes 20 volts to go on the red path, if I go backwards on the blue path, that's a minus 20 volts. That's the nature of conservative forces. That's the nature of the path independence. And so if you have a loop, you go from one point, you travel in a space, and you go back to the same point, you will end up with a potential difference of 0. This is a very important law in circuits that you'll see quite a bit. It's not just for circuits, but we're going to only apply it towards circuits. It's called Kirchhoff's loop law. And it says that if you go around a loop in a potential field, you will always have a potential difference of 0. 0. What, my goodness, why is my phone harassing me? Yes, I know I have a million meetings today. Leave me alone. All right, push it on. So, a particle follows the trajectory shown from I over to F. What is the potential difference here? The answer is C. We go from 0 down to minus 50 volts. The potential difference is minus 50 volts. Excellent. It doesn't matter, by the way, that we went up here. Okay, it's like saying, it's like rolling a ball, right, down a hill. And then maybe in the process of doing that, it goes up a little smaller hill, and then it comes back down. Well, that smaller hill, I mean, it's possible it doesn't get over that hill, right? That's a whole separate thing. But if it does, then so same thing here. Is it possible that, this thing was clearly able to get up to 50 volts? Then it went down to minus 50. But we don't care about that path. We only care about initial to final. Right. So this is a topic we talked about at the very end of our lectures leading up to the first exam. And so I remember this because I remember I wanted to have this slide actually there, but I don't because it mentions things you don't know about, like potential. That's why I didn't have it there, and I forgot that. So here is what conductors are going to do. Okay. A conductor, if it has charge on it, will exist, those charges will exist on the very edges, on the surface of the conductor. The electric field inside is 0. Therefore, the potential is a constant on the inside. The surface itself is an equipotential. In fact, the shape of the conductor is the shape of the equipotential. Everything on the inside has the same value of the potential. And then as you go outside of it, though, there's an electric field. The potential starts to decrease if we have positive charges like you see here, actually. If you obviously have negative charges, it will be different. The electric field will point in, okay? And it's going to be perpendicular to the surface. And on the corners, like you see here, the spacing between where the charges are going to line up is going to be a little bit more bunched up on the corners. And as a result of that, the electric field ends up being a bit stronger on these edges here. So that's what part of this is what we've learned before, but part of this is now more information because we know more things about potential here. So I think I'm going to end this up with a few questions for you. Or not. What's going on here? I don't remember my slides. Oh, yeah, the questions are as follows. Okay. And so I don't have much to say about this because this was kind of covered in lab a bit, but you could see the equipotential surfaces here. We could see the relationship between the field lines and the equipotential surfaces. If these are charged to, this electrode over here is charged at 50 volts. This one's at 0 for whatever reason. It's obviously, it could be charged, I suppose. It's probably grounded, though, which means the potential is set to 0. And we have these green dashed equipotential lines that represent changes of 10 volts apiece. And we can easily establish what our electric fields are like because as we travel from one location on the electrode to the other, we have to pass through these equipotential lines so that we are always perpendicular to the equipotential lines. That's the nature of the calculus behind this. That has to be maintained here. Excellent. So this is a nice complete picture of what's going on in the environment here. We have information about potentials and information about electric field. This is the pinnacle of really displaying what this system's doing from an electrical standpoint. Equipotential surfaces, electric field lines. I'm going to move on from this slide because I'm about to cry. I'm tearing up here. It's just so, it's beautiful, to be honest. Okay, these two questions are going to lead us, these two questions are a segue. it's gonna be a long segue because I'm introducing something right now to you, and then we're gonna be developing this as we move on here. Metal wires are attached to the terminals with 3-volt battery. What's the potential difference between points 1 and point 2? The answer is B. It's B. All right. Okay. Why? Why is it B? Okay. Now, a lot of you are like, it's not B because he said B. All right. Well, I might do that, but you know what? You got to stay strong, mentally strong. Okay. My instructor's playing mind games. I gotta focus. I gotta not let that bother me. All right. So here's what's going on here, right? The battery produces a 3-volt potential difference across it. Now, the top, the positive terminal of this battery, and the wire are a conductor. That is one long continuous conductor. That means the potential is the same all along this. At the bottom here, there's a negative terminal. Now, the negative and positive terminals are not connected to each other, okay? Just to be clear about that, like this is not a continuous connector. You should treat this battery as the upper portion is an electrode and the bottom portion is an electrode, and they're not connected as far as conductors. Because if they were, there'd be no voltage here, right? Everything would neutralize. The bottom is is the negative terminal, and the wire at the bottom is at the same potential. So everything up here is 3 volts higher than it is down here. That's it. Everything up here is 3 volts higher than it is down here, because these wires and the terminals on the battery are one continuous conductor. The answer is B here. Okay. Now, what happens though if I connect these? If I decided to pull this thing down, which I have a way to do that here actually. I have a way to do that. Here we go. What if I did this? What? Look at that. Not quite the same color. But as soon as you do that, guess what? New physics. New physics happens. You don't know what happens. You don't know what happens. If I connect these up, you don't know what happens. Okay? When I say you don't know what happens, I mean as a student that has no knowledge of anything else regarding circuits. This is a very important transition we're making right now. When I connect those wires, we now leave electrostatics and we enter into the world of circuits. Okay, we spent a long time establishing electrostatic behavior, and that is coming to an end. We dealt enough with electrostatics. Now we want electrodynamics. I don't like to use that word because it seems way more complicated when you just mention in circuits, but we're now going to circuits. Okay, so what's going on now? What's the potential difference up here now? What's the potential difference down here? You don't know. You don't know. Is it 3 still? No. We don't know. We need more information. Now, assume this wire has a small resistance and it's uniform throughout. What happens is the 3 volts starts here and it gradually drops and drops and drops and drops as you move along the wire. And when you get back to the negative, when you get to the negative terminal here, you are now 3 volts lower than you were before. But it's a gradual change here. Okay, gradual change here. The loop is this though. The loop is if I go from the positive terminal all the way around through the negative back to positive. Because if you just go from positive to negative, that's not a loop. That's not a loop. You still got this other section right here that you got to do. So if you go from positive all the way around back to positive, it is 0. It is 0. Last question. Last question. So don't worry about this too much. When I extended the concept here, you don't got to know that yet. We're getting there soon. Oh my goodness. Oh my goodness. So complicated. All right. Now, metal spheres 1 and 2 are connected by a metal wire. What's being displayed here is that they're different sizes. What do these spheres have in common? Let's see it. Let's do some letters. This is a big question. This is a good question here. Love this question. A lot of people talking about this question. People say it's probably one of the best questions that you've ever seen. D, A and C, huh? A and C. The answer is, you ready? A. Okay, now we got to talk about this. Because you might be like, I don't know. Okay, so the answer is definitely A. Why? Because 1 and 2 are connected by a wire. So 1 and 2 on the wire all form one continuous conductor. Okay? That's what we learned. That's what we just talked about. So the answer is A, simply because on a conductor, the potential is the same throughout. If it was not the same, then we have a potential difference, and that will generate a current. We don't got that here. Okay. So now, a lot of you said C, though. Let's see what's going on there. That was not meant as a pun, but it kind of turned out that way. Okay, so what's going on with the with these spheres here, right? What's the potential? K, Q over R, right? Well, let's do capital R. That's the potential on the surfaces here, right? Now, guess what? They are at the same potential, but they have different size radii, right? Therefore, the charge can't be the same on them. Okay? So the idea is that for a larger radius, you could have a larger amount of charge, as long as this ratio is obeyed. So this is a larger sphere, number 2. It has more charge on it. Number 1 is a smaller sphere, it has less charge on it. Same electric field? Well, no, right? Because, again, we just made that argument. So what's the electric field of a conducting sphere, outside of a conducting sphere? K, Q over R squared. If we evaluate on the surface, for example, maybe. Or close to the surface. Well, same deal, right? Different Qs, different electric fields, or different Rs. Okay. So, electric field's not the same. Charge is not the same, but the potential is the same. And now, why am I showing you this question? Okay, because I'm trying to communicate a point here. The point is this. Our focus from here on out needs to be about potentials now. Potentials. From a conceptual standpoint, understanding potentials is going to help us understand a lot about the behavior of things and some of the other quantities that maybe are a little bit more complicated to do. For example, if we didn't develop the idea of potential, right? And I asked you this question, but I put something else for A, you know? I just said we have electric field, we have charge, and I don't know, I threw something else up here. This would be a little bit harder to figure out. We'd have to do a Gauss's law kind of thing, is what we'd have to do. We have to develop the electric field for these spheres, and we'd eventually get the same, well, we get the answer that it's not B or C. But the potential is just making our lives easier. Not only is it more practical, but it's easier from a conceptual standpoint to understand what's going on.